Hello students, welcome back to the class of teacher Meenal Pereira. In today's session, we will be studying about Newton's laws of motion. So let's begin. Let's consider some situations. What could be the reason for the following events? A static object does not move without the application of a force. The force which is sufficient to lift a book from a table is not sufficient to lift the table. Fruits on a tree fall down when its branches are shaken, and an electric fan keeps on rotating for some time even after it is switched off. So here we are considering 4 situations. Now these situations, children, very often you must have observed in your daily life. Let's see what is the reason behind it. If we look for the reason for the above, we realize that objects have some inertia. Last year we have already studied about inertia. We have learned that inertia is related to the mass of the object. What is inertia? It is a tendency to do nothing or to remain unchanged. Okay, so until and unless any force is applied, an object tends to remain in the same state. That we call as inertia. So Newton's first law of motion describes this very property and therefore is called as law of inertia. So Newton's first law explains us about inertia. So widely it is known as the law of inertia. Let's see what is this law all about. Before that, let's try some activity. Fill a glass with sand. Keep a piece of cardboard on it. Keep a 5 rupees coin on the cardboard. Now strike the cardboard hard using your fingers. Observe what happens. Yes, children, you must have tried this. You tell me what will happen. What will happen is the coin falls in the glass. The cardboard is thrown away, but the coin falls in the glass. You must have played tug-of-war. So, as long as the forces applied by both the sides are equal, that is balanced, the center of the rope is static in spite of the applied force. As you can see in the diagram, this is tug-of-war, you must have seen. If we apply equal amount of force from same side or from both the side we apply equal amount of force, the center remains static. On the other hand, when the applied forces becomes unequal, that is unbalanced, a net force gets applied in the direction of greater force and the center of the rope shifts in that direction. Okay, so now suppose this side, if there are 4 participants, so what will happen? From this side, the force will increase. So what will happen is, obviously, the rope will get pulled towards this side or where there are more persons. Okay, so we say that now on the rope, the force is unbalanced. So that gives us Newton's first law of motion, which is also called as law of inertia. An object will not change its motion unless acted by an unbalanced force. So an object is not going to change its motion. That means if it is at rest, it will stay at rest. Rest means no movement. And if it is in motion, it will remain at the same velocity. So until and unless an object which is in motion or at rest is acted by an unbalanced force, it is not going to act or it is not going to change its position. Objects with greater mass have more inertia. It takes more force to change their motion. So as you can see in the first diagram, this is 300 kg. This is 30 kg. So more mass, more inertia. And obviously you all know that it will take more force to change its motion. So very simple, Newton's first law of motion. Now coming to the property of inertia. When an object is at rest or in uniform motion along a straight line, it does not mean that no forces is acting on it. Actually, there are number of forces acting on it, but they cancel one another so that the net force is zero. Okay, so we can't say that when the object is at rest there is no force. In fact, there are many forces acting on it, but it is from all different sides. So what happens is the net force becomes zero and therefore the object does not move. So Newton's first law explains the phenomenon of inertia. That is the inability of an object to change its state of motion on its own. Okay, so object will not change its state of motion. It also explains the unbalanced forces which cause a change in the state of an object at rest or in uniform motion. Okay, so when we apply unbalanced force, obviously there will be a change of state, and that explains us all the inertia examples. So all instances or all examples of inertia are of Newton's first law of motion. So I hope you all are clear about Newton's first law of motion. Moving further to second law. Now let's see what is Newton's second law of motion. So before that, let's see one small activity.
A. 1. Ask your friend to drop one plastic and one rubber ball from the same height. 2. You catch the balls. Which ball was easier to catch and why? B. 1. Ask your friend to throw a ball towards you at slow speed. Try to catch it. 2. Now ask your friend to throw the same ball at high speed towards you. Try to catch it. Which ball could you catch with greater ease?
Okay, so what you can see here in the first case, obviously the plastic ball is more easy to catch than the rubber ball, and in the second case what you can see is the ball that is coming with low speed is more easy to catch than the ball with the faster speed. I know you all are champion children, so for you in both the cases the ball will be very easy to catch, but actually what happens is the lighter weight ball and the ball that is coming at a slower speed is more easy to catch. So this is explained by Newton's second law of motion. Let's see what is that. The effect of one object striking other object depends on the mass of the former object and its velocity. It means that the effect of force depends on a property related to both mass and velocity of the striking object. Now both the examples we studied that both the balls has some mass and it is coming with some velocity. So that means this property is related to mass or weight of the object as well as the speed or velocity what with the object is traveling. So this property was termed as momentum by Newton. Okay, so what is momentum? This is a new property which is denoted by symbol P, and it is the product of mass and velocity. So when we multiplied mass to velocity, we get the momentum. So momentum has magnitude as well as direction. So it is a vector quantity. Its direction is in the same as that of velocity. In SI system, the unit of momentum is kilogram meter per second, while in CGS system, it is gram centimeter per second. So that gives us the Newton's second law of motion. The rate of change of momentum is proportional to the applied force, and the change of momentum occurs in the direction of force. Okay, so proportional means as the force increases, the momentum also increases. The force decreases, the momentum also decreases. And the rate of change of momentum is in the direction of force. Now let's see this with the equation. Suppose an object of mass m has initial velocity u. When a force F is applied in the direction of the velocity for time t, its velocity becomes v. The initial momentum of the object is mu. As we have studied, its momentum is mass into velocity. So mass m, velocity u, and final momentum after time t is mv. That is mass into final velocity. The rate of change of momentum is change in momentum upon time. Okay, so what is change in momentum? Final momentum, that is mv, minus initial momentum, that is mu upon t. Okay, so then removing m common in the bracket, we have v minus u and divided by t. But v minus u upon t is acceleration. We have already studied in the previous model. Therefore, this v minus u upon t gets replaced by a. So, ultimately what we get is ma. And according to Newton's second law of motion, the rate of change of momentum is proportional to applied force. Now, force is F. So, this ma is proportional to F. Now, proportional sign we cannot use. So, our next task is to remove this proportional sign. And how we can remove that? With the help of a constant. And here the constant uses k. Okay, so therefore we get the equation F is equal to m into a. That is, force is equal to mass into acceleration. Consider two objects having different masses which are initially at rest. These are the two masses with two objects with different masses at rest. The initial momentum for both is 0. Suppose a force F acts for time t on both the object. On these both the object, the force acting is for time t. Obviously, the lighter object starts moving faster than the heavier objects. But from the above formula, we know that the rate of change of momentum, that is F in both the object, is same, and the total change in their momentum will also be the same, that is Ft. Okay, so change of momentum is initial minus final momentum. Now here, since it is moving, or we can say that the lighter object moving faster, but the rate of change of momentum, that is, since the force acting on the same object is same, the total change in their momentum will also be the same. So, if the same force is applied on different object, the change in momentum is same. So, same force you applied on the different object, momentum will be same. Here I am not saying that it will move with the same speed. Depending upon the mass of the object, it will be fast or slow, but the momentum will be same. In SI system, unit of force is Newton. So, Newton is the force necessary to cause an acceleration of 1 meter per second square in an object of mass 1 kg is 1 Newton. In CGS system, the force is dyne, and dyne is the force necessary to cause an acceleration of 1 centimeter second square in an object of mass 1 kg is 1 dyne. So finally, we studied Newton's first law of motion, which says law of inertia. The object remains in the state of uniform motion until an unbalanced force acts on it, and Newton's second law of motion, where the rate of change of momentum is proportional to the applied force and the momentum occurs in the direction of force. Thank you very much and take care.